Hello guys, welcome to the 15th class of this course. In the last class, in the last few classes, we talked about the variational principle. There we solved some interesting problems regarding this variational principle. Then we derived the generalized Lagrange's equation of motion using that variational principle. So today we will solve some very simple and interesting problems using this Lagrangian equation of motion. Okay, so let's solve the first problem. So problem 1. Set of the Lagrangian for a simple pendulum and obtain an equation describing its motion. Basically, obtain the equation of motion of the simple pendulum. So first we need to write down the Lagrangian of a simple pendulum, and then we need to find out the equation of motion. So let's draw a simple pendulum first. Let's say a simple pendulum. So this, let's say this is the equilibrium position of this pendulum. So this is the path it is oscillating. So let's assume that it is at this point, it is at angular displacement theta. L is the length of this rope, M is the mass of the bob, and this is the support. So let's say this point is O. This point, the equilibrium position here, this point is A. This point is at point B, let's say, at when the angular displacement is theta, is at point B. And if we draw a perpendicular from this point B on the line OA, then this point is C. So then this length we will define as H, and this length will be then, so this is L and this is, so this line is L and this is theta. So this length OC is basically the projection of L. Okay, so in that case this OC will be L cos theta, right? It's the base, so it will be L cos theta, and the total length, it will be the length of the this wire, that is L. So it means H equals to L minus L cos theta, or if you take L common, it will be 1 minus cos theta. Now let's assume that this is our zero potential line. So here we are assuming this yellow line, we are assuming that V equals to 0. So here the potential energy along this line, it is 0. So in that case, when the angular displacement of this pendulum, it is theta, then it is at a height h from this line. So in that case, its potential energy will be mgh. So V at angular displacement of theta, it will be mgh, and h is L times 1 minus cos theta. Okay. So we have the potential energy. Now we need to find out the kinetic energy, because we want the Lagrangian, and Lagrangian is T minus V. So we need this potential energy, we need this kinetic energy. So for kinetic energy, let's assume that, so it is a coordinate system. Let's assume the y axis, it is pointing downward. So we can choose the y axis as we wish. And let's say it is the bob, is the pendulum at angle theta. Same. So in that case, L, the length of the pendulum, if it is L, then this length is L sine theta, and this length is L cos theta. So in that case, so this is basically y, and this is basically x. So we know that kinetic energy T is equal to half m x dot square plus y dot square. That is half m v square. V square means vx square plus vy square, and vx means x dot, vy means y dot. So in that case, from this relation, we can find like this x dot, it will be L theta dot cos theta, and y dot, it will be minus L theta dot sine theta. So if we now take this x dot square plus y dot square, we will get half m L square theta dot square cos square theta plus L square theta dot square sine square theta, which will be half m L square theta dot square cos square theta plus sine square theta, which is 1. So our kinetic energy will be T equals to half m L square theta dot square. So L is constant, and here the generalized coordinate is theta. So V, which is a function of theta, L, T, kinetic energy, which is a function of theta dot. Then the Lagrangian of the system will be L equals to T minus V, which will be half m L square theta dot square minus mgl 1 minus cos theta. Okay, this is a potential energy, mgl 1 minus cos theta. So we got our Lagrangian. This is the Lagrangian. So now the Lagrangian equation of motion will be del L del theta dot ddt of it minus del L del theta equals to 0. Then ddt of del L del theta dot. Del L del theta dot means there is no theta dot dependence in the second term of L. The theta dot dependence only comes through the first term. So if we take the derivative with respect to theta dot, it will be m L square theta dot minus del L del theta. So the theta dependence is only here. So in that case, it will be minus minus del theta of mgl cos theta equals to 0. So derivative of this term, this one, it is with respect to theta, it is 0. So only the cos theta, it will get the derivative. So ddt of this, so m and L, so in the first term, m and L is constant. It is not changing with respect to time. So ddt of this will be ml square theta double dot, and dd theta of this term, so cos theta, derivative of cos theta with respect to theta is minus sine theta, and there is a minus already in front of that, so it will be plus mgl sine theta equals to 0. So then theta double dot will be the angular acceleration, theta double dot, it will be g by l minus sine theta. This will be the equation of motion, and this is the Lagrangian. This is the Lagrangian. So now this simple pendulum will follow a simple harmonic oscillation if theta is tends to 0, value of theta is very small, then sine theta tends to theta. In that case, then theta double dot will be minus g by l theta, which is equals to minus omega square theta, where omega is root under g by l. So it's the equation of SHM. Then the pendulum will oscillate in simple harmonic motion, SHM. So in that case, what will be the solution? The solution will be theta at time t, it will be, so it's a second order derivative. So double dot means d2 theta dt2. So there will be two arbitrary constant. So a is one constant. You can write a to the power I omega t plus b to the power minus I omega t. It will be the solution. In this case, or in this case, if theta tends to 0, okay, if theta is very small, then this simple pendulum, it will follow a simple harmonic motion. Okay, so this was our problem 1. So the next problem, let's first write the statement of the problem. This problem 1, problem 2. Problem 2 is use Lagrange's equations to set up the differential equation of vibrating masses shown in the figure. And the figure is like that. So these are rigid walls, and there are spring, there is one mass, and there is a spring in between, there is another mass, and there is a spring, and it's connected to the wall. So these are all equal mass. So let's take M and M, and spring constant of every spring is K. Okay, so this is our system. So for this system, we need to first find out the Lagrangian, and then we need to find out the Lagrangian equation of motion. So it's this kind of system. These are very important systems. So we will encounter this kind of system in our later chapters also. So when we study the small oscillation, there also we need to find out the Lagrangian. We need to find out its equation of motion. Then we need to solve it, and we need to find out its normal modes of oscillation. Okay, so finding out the equation of motion is very important for these kind of systems. So let's say this is the equilibrium position of this first mass, and this is the equilibrium position of this second mass. And when it is oscillating for at some moment, its displacement from the equilibrium position is x1 at time t, and the displacement of the second mass is x2 at that time. So in that case, the potential energy of the spring, potential energy of the first spring. So in that case, the natural length of this first spring, it was elongated by this x1. Okay, so then the potential energy will be half k x1 square. So and the change of natural length, change of length of this second spring, the middle one, it will be x2 minus x1. So in that case, it will be half k x2 minus x1 square plus potential energy of the third spring. So its length is changed by x2. So in that case, it will be half k x2 square. Okay. So we got the potential energy of the system. Potential energies are coming through the springs. So it's spring potential energy. And the kinetic energy, T, it will be half mv square. And for this fast mass, its velocity is x1 dot, that means x1 dot square, plus for the second mass, its displacement from equilibrium is x2. So its velocity will be x2 dot. So half m x2 dot square. So these are the kinetic energy and potential energy of this system, spring mass system. So in that case, the Lagrangian L, it will be T minus V, implies this Lagrangian will be half m x1 dot square plus half m x2 dot square minus half k x1 square minus half k x2 minus x1 square minus half k x2 square. So this is the required Lagrangian. Okay, so we got the Lagrangian. Now we need to find out the Lagrangian equation of motion. Here notice that there are two generalized coordinates, which are x1 and x2. The two coordinates here, two independent coordinates. So in that case, there will be two Lagrangian equation of motion. One is del L del x1 dot ddt of it minus del L del x1 equals to 0, and another will be let's call it equation 1, and another will be ddt of del L del x2 dot minus del L del x2 equals to 0. This will be equation 2. So now let's solve equation 1 first. Okay. Equation 1. ddt of del L del x1 dot. So the x1 dot, that is only this term, okay? That x1 dot dependence is only this term. So in that case, del L del x1 dot will be m x1 dot. M x1 dot minus del L del x1. So there is x1 dependency in this term also and in this term also. So in that case, it will be, so there is a minus sign and also minus sign in the Lagrangian here and here. So in that case, we plus k x1 plus k x2 minus x1, and then derivative of this, it will be minus of 1 equals to 0. So in that case, it will be m x1 double dot plus k 2x1 minus x2 equals to 0. So the equation of motion will be, one equation of motion will be equals to minus k 2x1 minus x2. Let's call it equation 3. And from equation 2, we will get ddt of del L del x2 dot. So del L del x2 dot will be m x2 dot. So we will get ddt of m x2 dot minus, so again del L del x2. So for this last term, there is already a minus sign here. So it will be k x2. This minus and minus will cancel. It will be plus k x2. And here in the middle, in this term, there is also x2 dependence. So in that case, it will be plus k x2 minus x1 plus k x2 minus x1 equals to 0. So in that case, we will get ddt of this term, it will be m x2 double dot plus k times 2x2 minus x1 equals to 0, implies m x2 double dot equals to minus k 2x2 minus x1. So these are the two equation of motion. Let's call it equation 4. So equation 3 and equation 4, these are the required equation of motion for this spring mass system. So equation 3 and 4 are the required equation of motion for the spring mass system. Okay. Great. So today we solved two problems regarding this, two very important problems regarding this Lagrangian equation of motion. So now I will give two homeworks for you guys to try. So I will write down the few steps and the solution. So homework one will be use Lagrangians. So use Lagrange's equations. Use Lagrange's equations to describe the motion of a particle of mass m, particle of mass m, sliding down a frictionless inclined plane, frictionless inclined plane of angle alpha. Okay. So particle of mass m, it's sliding down a frictionless inclined plane of angle alpha. So for this system, we need to find out the Lagrangian first and then the Lagrangian equation of motion. So let's give some hints. So I'll give some hints. Let's draw the figure. Here, this is the inclined plane. The angle of inclination is alpha. So let's say at some moment, the mass is at this point. The particle is at this point. So let's say this is the zero potential line. So here the potential, initially the potential was zero, potential energy was zero, and this is our x-axis. So at this moment, the particle traveled a distance x. Okay, and this is the zero potential line. So in that case, if we draw perpendicular from this position of m to this line, to this vertical line, so in that case, this angle will also be alpha. This angle, because it is alpha, so this angle will also be alpha. And if this length is L, this length is x, so the particle traveled a distance x from the initial point. So in that case, this length, so the height it traveled down, that will be, if we call it by h, then this h will be x sine alpha, because this will be x cos alpha and this will be x sine alpha. Okay. So in that case, here the potential energy was zero. So now if a vertical distance traveled is h, so in that case the potential will decrease, and it is decreased by how much? mgh. Okay. So the potential at this point, so potential at this point of this particle, it will be minus mgh, which will be minus mgx sine alpha, and kinetic energy T will be half m x dot square. Now you will find the Lagrangian by T minus V. So now, and then if you solve the Lagrangian equation of motion, you will get the answer as x double dot, which is the acceleration of the particle, will be g sine alpha. This is the answer. So do the intermediate steps, and another homework is homework 2. So another homework is a double pendulum. So we have a double pendulum. Double pendulum vibrates in a vertical plane as shown in the figure. So I will draw the figure just after writing this problem statement. So problem A, so part A is write down the Lagrangian of the system. Write down the Lagrangian of the system. And part B is obtain the equation of motion. Obtain the equation of motion. So we have a double pendulum. We need to find out the Lagrangian and we need to find out the equation of motion. So I will do some intermediate steps and I will write the final solution. The rest of it you need to calculate by yourself. So let's draw the double pendulum first. Let's say this is the equilibrium position of the first pendulum. And this is our first pendulum. Okay. And this is the equilibrium position for with respect to the first pendulum. Equilibrium position of the second pendulum with respect to the first pendulum. And the second pendulum is set this point like this. Okay. So the generalized coordinates we need here is this angle theta1. So this we already talked about that when we are discussing about the generalized coordinates and the constants. So in that case we talked like what we should treat as generalized coordinates for the problem of double pendulum. So this is the angle theta1 and theta2. So these two will be theta1 and theta2. These two will be the generalized coordinates in this case. And this length of the first pendulum, let's consider it L1, and length of the second pendulum, consider it L2. This will be fixed. Let's say mass of this one is M1 and mass of the second one is M2. Okay. So we have our double pendulum system. So first of all, we need to write down the kinetic energy. We need to write down the potential energy. Then we need to find out the Lagrangian by calculating T minus V. And then we will write the equation of motion. So the kinetic energy of the system will be equals to, you need to do it by yourself. So I'm just writing the expression M1 L1 square theta 1 dot square plus half M2 L2 square theta 1 dot square plus L2 square theta 2 sorry, is L1 square, and this is theta 2 dot square plus 2 L1 L2 theta 1 dot theta 2 dot cos of theta 1 minus theta 2. And the potential energy, it will be M1G L1 plus L2 minus L1 cos theta 1 plus M2G times L1 plus L2 minus L1 cos theta 1 minus L2 cos theta 2. So this will be the kinetic energy and potential energy. And then you need to find out the Lagrangian by T minus V. And then you need to solve the Lagrangian equation of motion. So there will be two Lagrangian equation of motion because we have two generalized coordinates, two independent coordinates here, theta 1 and theta 2. Okay. There will be equation with respect to theta 1 and there will be another equation with respect to theta 2. The equation of motion will be the first one will be m1 plus m2 L1 square theta 1 double dot plus m2 L1 L2 theta 2 double dot cos of theta 1 minus theta 2 plus m2 L1 L2 theta 2 dot square sine of theta 1 minus theta 2 equals to minus of m1 plus m2 g L1 sine theta 1. So this will be the first equation of motion, and the second equation of motion will be m2 L2 square theta 2 double dot plus m2 L1 L2 theta 1 double dot cos of theta 1 minus theta 2 minus m2 L1 L2 theta 1 dot square sine of theta 1 minus theta 2 equals to minus m2g L2 sine theta 2. So these two will be the equation of motion. Okay, if you solve the Lagrangian, so in that case, you will find these two will be the equation of motion. So these two are the homeworks. Okay, so that's all for today. In the next class, we will talk about some more problems, some more very interesting problems of this Lagrangian equation of motion. Okay, thank you.